IDOT has done about 40 bridges and bridge decks, and that's been a both combination of microsilica and slag replacement. All have performed over adequate, I would say, Joe.
I would agree.
All without wet cure methods. So E5 internal cure is doing what it's doing. And as far as next year goes, I believe on the docket, what's getting ready to hit the presses in January, you're going to have a lot of contractors in Indiana looking at this just from the mere savings of wet cure aspect alone, from a price compatibility point for what E5 does for them. Once they start using it, they'll really see what E5 does for them in terms of strength and in terms of how you can save on that wet cure dollar amount and then time in construction. And I know you guys don't advertise that E5 increases strength, but as an engineer, what I've noticed is it does increase strength because it takes that water cement ratio that you've originally put into your mix design and it saves that water for the mix. You guys originally came up with what I think is monumental in this, we've already played with E5. I know it works, it's great. The thing that's different in this is the liquid fly ash. Can you explain a little bit of what I call particle packing and how liquid fly ash helps build that matrix in the science and how it goes through chemically into the mixture?
Well, first of all, liquid fly ash concept comes from the dealings of my background as a finisher, dealing with the inconsistencies of fly ash. Fly ash gives us finishers inconsistencies in set times, air, workability, and most of all, we don't know the type of quality we get of fly ash. So as I worked with E5 internal cure, I noticed the pozzolanic reactions and the chemical makeup of mimicking a fly ash. It gave me the idea of digging deeper into the chemistry and see where the fall off of the bell curve turned us from internal cure into liquid fly ash, into a pozzolanic state. And with that being said, when we headed down into that endeavor and we found out that going over that bell curve and started to getting better pozzolanic reaction, I noticed what we were getting was a pure type of fly ash in some sense of form. We were getting the set times consistent, the air was consistent, the workability was consistent, the mixes came out repeatable time and time again. Therefore, we got the best of fly ash now without all the side effects of a fly ash. So that was the premises behind that, to give us a cementitious replacement that we could count on as a finisher's point of view. To a ready mix guy, that can go many different ways. Frees the silos up if they went to this type of method of a cementitious replacement that would give them customers other options for cement, a type 3 or type 1-2.
Or even a slag.
Yeah, it gives them versatility.
Versatility in what they already have.
In what they already got. So today is very important because this is the actual first liquid fly ash placement in the state of Indiana. This will be talked about 20 years from now, how today changed and shifted the pendulum for the concrete industry. And it's finishers and contractors like Dan and myself that are not afraid to take the risk with new technologies. We embrace it, we like the challenges, and today is a very special moment for E5.
There's so much cool stuff going on that you can't even jump from one to the other because nobody's really understanding. First of all, we're just trying to get what E5 does and the way it controls. We make the water behave.
Let's talk about why you did this. Well, first of all, why did you do this? Why are we doing this overlay today the way we're doing it? Well, first of all, DOT here has a very, I will call, well, how would I want to describe their mix?
Aggressive,
and
temperamental.
I will say dangerous.
Yes. Yeah.
It is very dangerous and aggressive to a contractor because the recipe that they have given you gives you problems from the onset.
Yes.
It's too rich, it's very aggressive,
right.
And it's already being prepared for problems. The problems are coming straight out of that truck. When it hits the ground, it is going, hello, I'm awake.
Right, and you know, I've talked to you before about you know, nuclear testing, chain reaction type stuff, and they have this term that when you reach critical mass, or you're doing tests on critical mass, they call it tickling the dragon's tail. So when you make that critical mass, that's when everything starts happening.
Yep.
So there were scientists in Los Alamos that would go as close as they could, and that would be that'd be tickling the dragon's tail. And you get the same thing with what I'll call the standard mix that's in the book, is you're tickling the dragon's tail every time you pour it. Because instead of knowing you have a material you can work with like this, you have a material coming out and you start thinking about things. Is it too sunny? Is it too windy?
Yep.
I mean, not even normal concrete things like, is it going to rain in the next hour? Just
Right.
things like, is it too sunny? Is it too windy? What's my humidity? Am I going to be cooking off my moisture? And that's a lot of stuff to worry about.
Too much guessing game going on with that mix.
There's a lot going on.
So what happened was you started pouring with E5.
I started pouring with E5.
You started seeing the benefits of it in May, and then your thought patterns started turning.
Yeah.
And you're thinking, what, man, if this stuff does
What else
this,
can I
it
do with
does
this stuff?
Exactly. So now we get in and E5 liquid fly ash comes along. Oh, holy cow, what's this? Oh, pozzolanic reactions. Oh, we
Exactly.
can do this. So now this overlay today here, in our professional opinion, as contractor finisher, is a recipe for success.
Yes.
You're going to get a better outcome from this because it's easier to manage. Your crews are going to be better mood because it's easier to manage, and they're not having to play guessing game or always nervous or on edge because they don't know what the mix is going to do when it has silica fumes or latex or those high-powered cements that they're using.
And
So-
you tapped on it when when we're doing a bridge pour or we're doing an overlay pour like this, and we know we've got a high microsilica content. You notice how everybody's on edge.
Oh, all the time.
Because it wants to flash set or
Yep.
snap in a hurry before you can get anything done to it, including covering it. But this is, as you can see, we're not going to cover it.
Nope.
We're going to leave it here. There's about a 15-mile-an-hour wind out today, which would make covering it right now kind of a bear.
Evaporation rate's right now about 1.11.
Yeah.
So we got a nice little lift.
So we're there. We're under our 0.2. Although with E5, I really don't think it matters. The way it locks in, as you can see, even when they're pouring, or you can see it right now, there's no bleed water.
Nope.
So that tells me there's no water coming to the surface. There's no water to evaporate away. It's still got that nice glossy mix. I mean, it's holding on to that moisture. So, that's what the E5 is doing, and what the liquid fly ash is doing is replacing that cement and then adding that pore structure in there that makes it less permeable, and that's what I like.
Yesterday I got the question and goes, are you a fly ash replacement? And are you the same as fly ash? Do you fall underneath ASTM 618? And the answer was, no, I don't fall under ASTM 618 because I'm not powder. I'm a liquid.
Right.
And liquid is much different than powder. So I fall underneath my own standards of what we're replacing. And it's hard for them to wrap their head around there because they're so used to seeing powder. Oh, powder, there's no way that can work. Well, let's talk about surface area.
Oh yeah, all surface area. So when you get into it, when you look, and there's some other people out there that have some great information. Dr. Tyler Lay is one. I started looking at his triangle a long time ago, not only in an optimized mix design, but when you're looking for pozzolanic reaction versus surface area, you look at some of these SCMs and you say, well, we've got a slag, we've got a fly ash, and we've got a microsilica. And then you can look at what that does, and the reason we use some of those as replacements or in additions. So in this particular mix, what we've done is, and generally we've seen that, it more models what you can do with a fly ash because we've taken this liquid admixture and we've replaced 15% of our cement content. So like I said, on this mix here, it's about a 577 cement, but with a 15% replacement, it's gonna act like a 600. So that's what we're finding out in situ conditions, because as you can see, this mud slab here was actually poured, this overlay dam is what they call it, was actually poured about a week ago, and the strengths we were getting on those are close to 6,000 in a 6-7 day period. So that's acting real close to a 600-pound cement. And so people ask us all the time, And why do you want to lower the cement? And there's so many benefits, and I think we just went over, well, we reduce shrinkage. We're reducing cement, so we're reducing cost. For those of you involved in green technology out there, if you're reducing 15% of your cement content, you're also reducing carbon emissions, which in 20 years, this is going to be a carbon sink anyway. So we're doing a lot of good for the environment, along with saving money and providing a better product. So at a 3-day break, the patches with the same mix, we're getting around 3,700 PSI, which is pavement all day long. What we're hoping to make for the NDOT mix is you normally want to see 4,500 PSI for their micro overlay in 7 days. And we've met that with ease. So that's one thing we did when we looked at this mix. We said, well, we want to change the ingredients out to make it more user-friendly, but we don't want to change the application. We want to keep it we want to keep it as low permeability as possible to prevent chloride intrusion. If we do have chloride intrusion, we want to prevent that from spreading, which is what I went through earlier with our bonding agent that's also a corrosion inhibitor. Mm-hmm. So we've tried to cover our bases on that. We went with a flat surface to limit reflective cracking because our cracks are evil in our overlays because that's where chloride penetrates. So we're trying our best to limit all those scenarios while keeping in touch the original intent of the overlay, which is meant to be a wearing surface, so you want a good hard surface, which your hardness numbers with E5, just because of that particle packing in liquid fly ash, it's a harder surface anyway. So we've done that. We've decided to tine this rather than groove it. And there are reasons I'm not concerned. One of the reasons to be concerned in the past is if you look at this and you think thermodynamics, when you tine something, you've just opened it up, you've made it a heat exchanger, right? It's a radiator. So you've got all this surface area. We were talking about surface area. So in the past, if you had all this surface area and you've got this wind and you've got low humidity, you have a runaway effect for evaporation, which has always been an enemy of the finisher, the contractor. Yep. And most of that's due to plastic shrinkage. So that's the reason I timed this with E5, because you lose that risk of evaporation. And then the other reason I wanted to do this is because the state standard right now for overlays is grooving. There's a couple reasons they did that. One is for sound. Traffic engineers like it for sound. Another reason they did it was to limit the human problem of not covering it quick enough, not getting a cure on it quick enough. But what I don't like about it is once you open up those grooves, you cut through the cement, that's fine, your cement's treated. Right? You've got your microsilica in there and you've got a high cement content in there, but one of the unintended consequences of grooving is you're also opening up that aggregate. So when you open that aggregate, you've just defeated the purpose of protecting your cement mixture with all this stuff about porosity, because now if you have porosity in those aggregates, where do you think the chlorides are going to come in? So right here, that's what we're doing with all this. When we're tining it, we're allowing all that creamy, dreamy cement material to coat that aggregate still. And as you can see, you've got no exposed aggregate here. It's all cream covering that, and E5 helps a lot, like I said before. Joe doesn't advertise that it's a viscosity modifier, and doesn't claim to be, but that's what it does. And that's what it helps with. So it's not only just the internal cure faction that makes it wonderful, it's everything else, the side effects from it. For once, we have a chemical admixture that enhances the side effects rather than trying to treat one admixture with another admixture to counteract what the negative side effect was. So you put E5 in here, you have internal cure. The side benefit is it pumps easier. It finishes easier, just because of those viscosity modifying admixture effects. And then you get the particle packing, which I like, so it's a more dense product, which means permeability is going to go down. You get all these beneficial side effects out of one product. That's what I really like. That's what interested me when I really started looking at the science of it in early May when we started looking at this stuff. And I said, this is different. This is really different. The first thing I was amazed was when we tried NDOT's mix with 708 pounds of cementitious. We had E5 in it, and it was just a hotter than Bell's day, 20-mile-an-hour winds, and I thought this is really going to put them to the test. And we poured a flat section of overlay about that thick, and we didn't treat it with anything. And I waited for cracks to form that day, that night, and they never did. And that to me said, well, that takes care of our evaporation issue and plastic shrinkage. What else can this stuff do? And that's when we really started to play with
Yep.
it. And I think one of the best things that's come out of DOTs for this is they're learning more from you guys because you were more apt to get into commercial flooring first. So the commercial flooring, the things you did in commercial flooring, well, why did you do it? Well, we didn't want to cover it up. Number two, well, we wanted to get a good hard surface on it,
Yep.
pan on it earlier. We wanted more consistent mixes because you got tired of a guy riding a machine over there when he needed to be here, and then in 2 minutes he needed to be back over here because that's the way it was going. So that controlled release of the water in the hydration process. I mean, there were so many benefits to that in commercial world, and you just said, well, let's try it in normal concrete for a DOT. And now we're finding all these things, and that's what's really been great about specification products having so much knowledge in the commercial world. And Larry Arthur, who works for you, has an incredible amount of knowledge in the commercial world. And then what I enjoy doing is looking at the applications that you guys use in commercial world and say, well, how can I make that better in the DOT world? And vice versa. You've asked me questions.
Yep.
Why do you do this?
Yep.
And I say that, and you say, oh, okay, well, that makes sense. There's a shared experience in learning that you can get there that even sometimes in school in engineering, you pick a path. You either do bridges or you do buildings. So, but with this, it's a bunch of shared information, a bunch of shared technology, which is really great.
Oh, brings the industry together.
Yes. Never mind, I'll just talk.
Hey, so
So,